Well, let's begin. Alright, so we're at class 20, and we only get up to 28 by the end of the semester, and one of those is an exam. So we're definitely starting to see the light at the end of the tunnel in this case. Looking at the announcements, I don't think that's right about the homework assignment. Homework 8 is due on November 3rd. Oh yeah, that is right. Okay, I thought maybe the date was wrong, but yeah, it is Tuesday, November 3rd. So that homework assignment is posted now, and what we're going to do today is continue talking about some information in Chapter 5, the continuity equation, and we're going to specifically look at an idea called the Reynolds transport theorem, and it's maybe a more formalized expression of the idea that accumulation is the difference between in and out. So before we get into that, are there any announcement related questions that you've got? Okay. So here's the Reynolds transport theorem, and you may remember seeing this figure in our last class meeting where what we were doing was keeping track of some control volume that was essentially the volume inside of control surfaces. And the control surfaces were those outside locations where we were tracking the flow in and flow out of a system. And what we defined the system as was it was a continuously connected number of particles, and the number of particles that were in the system stayed the same over time, but the location of the system could change, and the shape and location of the control volume could also change over time. So what the Reynolds transport theorem tells us is that we can keep track of the mass in the system over time by examining the flow through the control surfaces. Here CS stands for control surfaces, and what we're saying is that if we have some cross-sectional area like the inlet pipe and the outlet pipe, if we have some cross-sectional area, then we can track the velocity through that area. And of course, we already know that volumetric flow rate Q is V times A. But then multiplying that by density, by rho, gives us now the mass flow rate. So last time in class we started talking about how m dot, the mass flow rate, which typically has units of kilograms per second, is a way of tracking the mass in the system mass and its location over time. So what the Reynolds transport theorem says is let's consider these control surfaces and do an accounting. Let's do an accounting of the flow in compared to the flow out through those control surfaces, and then also let's consider the change over time inside of the control volume. And so this d dt is saying inside of the control volume we want to see how the volume of fluid is changing. And so here I want to just point out that the V with the strike through the center, that is to differentiate volume from velocity. So in the control surfaces, the V in that variable means the velocity of the flow through the pipes that are going in and out of the control volume, whereas the V here, we're talking about the change in volume that occurs when there's a net imbalance between the inflow and the outflow. You'll notice that the change in volume is also multiplied by the density, and that turns it into a change in mass over time. So if the system is not going to have particles destroyed or created, if we assume that this is a conservative situation where there isn't a chemical reaction occurring and that there isn't a destruction of mass, ultimately what we're going to do is we're going to cancel out the left side of this equation. We're going to say that the mass of the system is constant. But the two broad terms in this Reynolds transport theorem are the storage term and the transport term. And so what we're going to say is that the net change in storage inside of the tank is due to an imbalance in the flow in versus the flow out. So we can account for the rise or fall of the water surface by tracking over time the inflow versus the outflow. So our variables here. M, of course, is referring to mass, and all of the other variables we've used before. And I'm just going to point out once again that we differentiate here between volume and velocity because we have each in the Reynolds transport theorem. But this idea is that we're going to look at the rate of change of any property related to mass, such as mass itself, as the difference between the transport and the storage. And so when there isn't a creation or or destruction of the system, when it's some particles that are going to persist in the environment, then this left term is zero. There isn't a change in mass over time. Now when you get into environmental engineering or other topics where there's a chemical reaction, then there will be creation or destruction of mass inside of the control volume. And the control volume may be a reactor of some sort. It may be a reactor where you're producing a chemical, or it may be a destruction reactor where a waste product is being consumed. And so it's not always the case that we're going to set this left term equal to zero, but here we will. And so what that now says is that the rate of accumulation inside of the control volume is equal to the net flux out through the control surfaces. So the other way to say that is that the change of mass in the control volume over time is the difference between the inflow and the outflow. And this is if there isn't a reaction occurring inside of the control volume. So we keep track of the mass in and the mass out. And that's kind of what we did when we were looking at that reservoir example at the end of Tuesday's class, the Oahe reservoir, where we had flow going in, flow going out, and we were essentially finding out how long until the reservoir was emptied down to zero stored water, and we solved for the time. So that's just one illustration of the types of problems that we can solve with this Reynolds transport theorem equation. More generally, we can use the Reynolds transport theorem to apply equations that otherwise may be numerically a little bit challenging if we were going to be tracking all of the particles in a system. And so you may remember that we talked about Lagrangian and Eulerian environments when we were talking about streamlines and streak lines. And so when we have a nozzle that's decreasing in diameter, like is depicted here, when the water is flowing through a big pipe and it's necking down to a smaller pipe, so the water is flowing from A towards B, and you can see that it's along a streamline. If we want to find out how the pressure is going to change because of this adjustment in the velocity, we have two approaches that we can actually take. I think all of us recognize that if it's steady flow, then that means we have non-uniform flow. And so Euler's equation could be used to predict what the change in pressure is, because an individual particle, as it moves from A to B, is going to be experiencing local acceleration. Its velocity is changing with respect to time if we track just the individual particle. So we're not talking about the entire system that's at a steady state, but if we have individual particles, we can apply Euler's equation to find out how the pressure is changing between the 2 points. Maybe more generally, what we would think is that this is a Bernoulli's problem. If we have steady flow and we're applying it along a streamline for an incompressible fluid, then Bernoulli's equation would say that because the velocity increases, the pressure is going to decrease. And so that would be another approach to finding the pressure at B. And that would be not just looking at an individual particle, but it would be looking at the system as a whole. But the problem with either of these is that there are really a lot of different path lines. If we do some sort of an analysis to try and track the trajectory of particles as they flow through the system, and we notice the chaotic and random behavior of those particles, it's going to be especially difficult to keep track of all the different places that they're going, and that's especially true if we have unsteady flow, and if the flow rate is increasing or decreasing, then that would make widespread calculation that much more complicated. And so sometimes, rather than tracking the individual particles, our approach is to divide the flow field up into a mesh and apply what we think of as the Eulerian approach, and that is that you treat each element in the mesh as an individual cell where you apply the free body approach to each of those cells. And you're looking at the pressure and shear stress forces that are acting on each individual element inside the control volume. So what we'd say is, what are the forces that are acting on just one of these boxes? The momentum that's flowing through it, the shear stress by the part interaction with the elements on either side of it, and because there would be fewer elements to track than each individual particle, then we could let each cell represent essentially the fluid that was inside of it, and the characteristics of every particle inside of that mesh would be represented by the cell. So the Reynolds transport theorem can be applied to relate these equations, like Euler's equation and Bernoulli's equation. It allows us to apply those equations to environments where we're doing our modeling in a mesh and where we're breaking up a flow field into individual elements. So that's just maybe one of the, a quick glimpse at one of the applications of the Reynolds transport theorem. As a just an additional practice on how we apply this idea of mass flow, let's consider a new reservoir. We have water that's coming in through, you can see the dashed line as representing a control surface. And so what's inside of that control surface is a tank, and it's open to the atmosphere, and it looks like it does have some headspace, and so the liquid level could be rising or it could be falling. Sometimes it's the case in an enclosed pipe, we say that there's no capacity for storage. You know, if a pipe is already full, then a liter in forces a liter out. But here that's not the case. This reservoir isn't full, and so it may be that the water level is rising, or it may be that it's falling. So our task here is to find out the velocity and the direction of the rise or fall. So you can see here that the tank diameter is described as 0.5 meters, and so that's talking about the diameter, the top view. If we were looking down from above, the diameter of this circular tank would be 5 meters. And we're going to use that to find how quickly the water level is rising or falling, because there will be a difference between the flow in and the flow out. This is water, and the density of water, of course, is 1,000 kilograms per cubic meter. But we know some properties of the jet that's coming in. There's a stream of water coming into the tank, and the cross-sectional area of that stream is 0.0025 meters. And you can see the velocity as well. So what you need to do is calculate mass flow rate in, and the mass flow rate out is already given as 3 kilograms per second. So let's find the rise or fall of the liquid level with the given diameter of 0.5 meters. Hopefully that gives you the clue that you'll need to calculate the cross-sectional area of the tank as well. But let me pause for a moment and give you a chance to do these calculations and let me know, is it rising or falling? Is there more water coming in or more water going out? And then what's the velocity of the liquid level? All right, well, let's take a look at the calculations here. That's right, Gavin, good. Okay, so we've got this tank, and the diameter of the tank is 0.5 meters. And so we can calculate the cross-sectional area of the tank using pi d squared divided by 4. And we're going to need that at the end when we find out the velocity of the water rising or falling. In this case, it's rising. We have the velocity of the jet that's coming in and the cross-sectional area of it. And so the flow-in calculations are just that we can know on a volumetric flow rate how much is coming in. So it's, you can see 0.0175 cubic meters per second, which is the result of our multiplying 7 meters per second by the cross-sectional area. And then to know the mass flow rate in, simply multiply the density by that. So it's 17.5 kilograms per second is the mass flow rate that's coming in. Mass flow rate out is 3 kilograms per second. Did it just say that directly? Yeah, 3 kilograms per second was already given. I think I've maybe changed this example over the years a little bit. So it's given as 3 kilograms per second, which means that the net accumulation is the difference between the in and the out. So the net accumulation is 14.5 kilograms per second. And that means that the liquid level has to be rising, because the mass in the control volume over time is increasing. So the liquid level is rising. And so what's the rate that that liquid level is rising? Well, the accumulation on a volumetric basis, we have it in the mass terms, 14.5 kilograms per second. We can put that back into volumetric terms, and that tells us that it's 0.0145 cubic meters per second of accumulation, which means that the rise of velocity in the tank, we can use the same Q equals V times A, or in other words, the velocity of rise in the water is the net accumulation divided by the cross-sectional area. So think about it. If you have a really large cross-sectional area, if this tank was a really big diameter, the liquid level would be rising more slowly than if it's a small diameter tank. And so in this case, you can see that the cross-sectional area is down here in the denominator. So the bigger the tank, the smaller the V rise would be. But for the situation that's described here of a 0.5 meter diameter tank and the area that gives us, then that means that the rise of the water is going to be 0.0738 meters per second, or essentially 7.4 centimeters per second. So it's going to be rising relatively slowly. And if you've ever filled up a swimming pool before, then you've probably seen firsthand the effect of how slowly the liquid level rises compared to if you had that same flow rate going into a smaller container like a bucket or even a bathtub. The liquid level is going to rise much more quickly because of the area. So that's kind of akin to the example that we had on Tuesday, where the liquid level was falling really slowly in the case of that Oahe Reservoir because it has such a big area. Okay, so any questions about this simple example having to do with liquid accumulation? I think maybe the one complex idea here that sometimes students don't initially think of at first is just that the velocity of the rise, meaning the speed that the liquid level is going up, that can be calculated with the accumulation divided by the cross-sectional area. So V is Q divided by A, even when it's talking about the rise of velocity inside of a tank. So it's the same continuity equation, but used in a slightly different way. Okay, now consider this tank. This is maybe just kind of a conceptual example here. You have a tank of water, and you can see that the liquid level is unknown. We want to know what's happening to the water level in this tank. And what's happening is that the piston at A is sliding to the left at a velocity of 2v. And you can see that we're given that the diameter of that piston is 3 centimeters. And so it's a circular piston, and the diameter is 3 centimeters. Now the piston on the right, which is here at location B, that's moving also to the left, but it's going at half the velocity that this piston A was. Instead of going at 2v, like piston A, piston B is moving to the left at V. So the question is, what's happening to the water level here? And I guess, broadly speaking, there are three possibilities. Either the liquid level is falling, or it's rising, or it's staying constant. And in a normal semester, we'd do a vote. We'd raise hands and see which of you thinks the water level is rising, which of you thinks it's falling, and which of you thinks it's holding steady. And I won't ask you to put that into the chat box, because I think inevitably a handful of students feel kind of silly when they at first say, well, the liquid level has to be constant, right? And they just, without thinking too much about it, just that first maybe knee-jerk reaction is saying, Well, the diameter at A is half the diameter at B, but it's moving at twice the velocity, and so it must all equal out. But that is not correct. Does anybody, so it's not holding steady. So let me ask you this, and I will ask maybe for your input with the microphone or type it into the chat box. Do you think that the water level is rising or falling? I've already told you it's not staying steady. Caleb says rise because B is 4 times bigger, and that's exactly right. Although the diameter is double, the cross-sectional area is 4 times larger at B than it is at A. Because remember, area is pi d squared divided by 4. And so doubling the diameter makes the area 4 times bigger. All right, so that means that you've got more water coming in than going out. And so let me just show you kind of the conceptual calculations that accompany this. We are given numeric values for the diameters. And so we can calculate the area at A and the area at B. And then we're going to do this checking the inflow, checking the outflow, and what's the net accumulation. That same idea of finding out what's the mass change inside of the control volume. And so the flow in is caused by the piston at B. And so the flow in is the velocity in, which is just V, multiplied by the cross-sectional area at location B. So that's the one with the 4 times larger cross-sectional area. And so we know the flow in terms of the unknown velocity V. So it's expressed as a variable, but the flow out is also in terms of V. And so what you can see is that the flow in is double the flow out, even though the velocity at A was twice. And so there's still more water coming in. So the net accumulation inside of the control volume is going to be a function of both the density of whatever this fluid is and also the velocity. But regardless of either of those things, whether it's a very dense fluid like mercury or a less dense fluid like an oil, it's a net accumulation, and so the liquid level is increasing in the tank. So it's important to pay attention to the area through which the volume is flowing. So these control surfaces, you had a much larger control surface at B than at A. Okay, now this is a kind of a tricky example. And this is one that for a lot of years I included as a homework assignment, this particular problem. And now I think I've replaced it with something that has related ideas, but it's a different question. There's a cylinder that's falling downward through the fluid. And we know that it's a circular cylinder having the shape of like a can of soup or something. The diameter of the cylinder is 150 millimeters. And so you can see that the dimensions are provided there of the diameter of the cylinder. And the tube that it's falling through, this pipe that's full of water, has a diameter of 200 millimeters. So we want to know what is the velocity of water between the two. And so the space that I'm talking about is going to be donut shaped. So think about, try and visualize in your mind, if you were looking from above, what's the top view look like? We have a pipe and a cylinder falling down through the center of the pipe. So it's like a ring or a donut shaped area through which the water is falling. Now as this falls downward at 1 meter per second, it's pushing water out of the way. And so the cylinder falls down and the water is pushed out of the way and around the side in order to make room for the cylinder to fall down. So we can use this control surface and control volume approach by drawing a control surface and saying, let's keep track of the flow in and the flow out through the control surfaces. And so the cylinder, as it's falling down into the control surface that we draw, is going to be pushing water out through the other control surface. And so let me just show you a picture. I'm not going to show you the whole solution quite yet because I'd like you to do these calculations, but let me show you what the control surface looks like that I drew, and that hopefully will give you an idea of how to proceed on the calculations. Let me just move forward to that. Okay. That's pretty small, right? Let's make it a little bit bigger. Okay, so the control surfaces are those dashed lines that are the locations where we're tracking the flow in versus the flow out. So what I'm saying is our control surfaces should be drawn so that as the cylinder falls down, it enters the control volume and it pushes water out, kind of like the way a syringe works. If you think about the plunger on a syringe is entering the volume of the syringe and it's pushing the water, or whatever it is, through a needle. Well, here, instead of pushing it down and out through a needle, the water that gets displaced by the cylinder entering the control volume is flowing out around the edges. And so what I'd like you to calculate is what is the mean velocity. So what is the V of the water that's flowing through that ring, through the ring-spaced shape that is between the cylinder and the pipe. Okay, I'll pause for a second and allow you to do that calculation. You're going to need to know the cross-sectional area of both the cylinder and also the pipe, and then consider the difference. Okay, so in the chat box you can see that some of your classmates have made it through. If you're still working on it, that's okay. We don't all work at the same speed. I myself am generally pretty slow at doing calculations, especially when I double and triple check them, which is kind of my OCD trend anytime it matters. Let's take a look at this one. Let me pull the solution up. I've already showed you what I think is maybe the trickiest part of a problem like this is conceiving of the geometry where to put the control surfaces. And so if we're applying this idea that we're tracking flow in versus flow out, then it makes the point that flow in can be more than just liquids, because this is a solid cylinder that's falling downward. And so what's causing deformation of the fluid is that the cylinder is falling down and pushing water out of the way. And so the cylinder is entering, in this case, a stationary control volume. And as the cylinder enters the control volume, since there's no capacity for storage, if we have this control volume being like a fixed region in space, as the cylinder goes in, the water has to be squirted out. All right, so first things first, looking at the cross-sectional area of the cylinder based on its 150 millimeter diameter that's given, then that defines the area of the cylinder. And it's falling down at 1 meter per second. So then that tells us essentially the flow rate. And we can determine the flow rate not just for a liquid. Here it's a cylinder that's made out of a solid, but this is going to be the same flow rate that the water is going out through that ring-shaped edge on the outside of the cylinder. And I kind of show what it looks like. You know, here's the top view where we're looking from above, and you can see the 0.2 meter diameter pipe and the 0.15 meter diameter cylinder, and so it's the net area that the water's going to be flowing through. And inside of the pipe, since it's already full of water, then that means there's no place that there can be an accumulation of fluid. So the flow into the control volume is equal to the flow out from the control volume. And so that means that this same 0.0176 cubic meters per second is what's going out around the outside ring. And then we're going to use this formula to find the velocity of the fluid. And so this is kind of the same reconfiguration of the continuity equation that we used when we were finding how quickly the water level was rising in a tank, right? We were looking at the net difference between in and out, and then the cross-sectional area through which the flow was occurring. And so here, the velocity in this ring shape that's outside of the cylinder but inside of the pipe, the net area you can see is 0.0137 meters squared. And so the velocity is that the water is going to be flowing up at a velocity of 1.29 meters per second. So sometimes the tricky part is just setting up the control surfaces, and it's not so much that in versus out causes accumulation. And that's generally a pretty natural idea that comes easily to people. But the tricky thing can be applying that to the picture at hand. What if the mass is cone-shaped? So if the cone was tapered at the bottom and had its widest part at the top, then I think what that means is that the fluid would be accelerating as you got closer to the end of it. So the velocity would be relatively low down at this part, and it would be getting faster up above. And so at each point, you could calculate the velocity by finding out what's the area of the cone at that section. That's an interesting question. Maybe I should put something like that onto the exam. I won't. All right. In the lab last week, we looked at the orifice experiment. And remember, the orifice equation is derived from Bernoulli's, and where we have a tank of water and a jet is going out, and the velocity of the jet can be determined by square root of 2gh, and this square root of 2gh is just rearranging Bernoulli's equation between the top of the water surface, where there's no pressure head, where there's no velocity head, and the outside jet, where it's also no pressure and equal to our elevation datum. If we rearrange that, we can find that the velocity of this outflow jet is equal to the square root of 2gh. So this just came to us from Bernoulli's equation. And so formulas like this, the Reynolds transport theorem, we can sometimes be asked questions like, how long will it take for the tank to drain to a certain level? And the time is going to be complicated by the fact that the velocity of the water that's flowing out is going to be gradually decreasing as h continues to fall. And, looking at this picture, it's clear there's no flow in, there's only flow out. So that means that the liquid level is going to be getting lower and progressively lower, and as it decreases, then that means that the pressure just outside of the orifice is reduced. And if the pressure is lower, then that means the velocity of the jet is going to decrease. And so in the class that we have on Tuesday of next week, we're going to examine some examples that ask us to find out how long it takes for the liquid level to fall a certain height by combining together the orifice equation and the Reynolds transport theorem. I wanted to take one quick look at one of the homework problems that you have on the next assignment that's due on Tuesday. So this is on your Tuesday assignment. This is problem number 8. And I just wanted to make sure that we're all on the same page with what this word equilibrium means. Equilibrium. So it says when equilibrium is reached in the 3-meter diameter oil tank, and so this is a circular tank, and the 3 meters it's talking about is, if you were going to do a top view of the circular tank, the diameter is 3. So it says when equilibrium is reached, what is the height h? Okay, so anybody want to explain what I mean by equilibrium here? What is equilibrium? Caleb's right. Caleb says inflow equals outflow. Jeremy's got it too. Inflow equals outflow. So in this problem, what you need to assume is that the flow in and the flow out are equal. So if we look, there's two streams in and one stream in and two streams out. Okay, so we know the flow in on a mass flow rate basis, kilograms per hour. And then one of the pipes, we know the velocity of the stream and the diameter of the pipe. And then we have an orifice here. And we're trying to find out how deep the water is. And so you're going to be solving for h with this square root of 2gh equation. So the velocity of the jet out of the bottom of that tank is determined by the square root of 2gh. So that gives you the v. And the area of that opening can be determined by the diameter that's known. But this word equilibrium is the key that tells you in equals out. So what we're looking for is what height of this oil is going to give you the outflow needed in order to keep the liquid level steady. So we want the one in stream to be equal to the two out streams. And what is the h that would cause that? Okay, so I just wanted to make very plain what I meant by this word equilibrium. I already told you today one of the important applications of the Reynolds transport theorem is in environmental engineering. And even if you're a mechanical engineer, there's a chance that you could work on some sort of a job at some point in your life having to do with water and wastewater treatment, because there are a lot of mechanical systems in a wastewater treatment plant. This is a diagram of a wastewater treatment plant, and it's actually kind of a miracle of modern engineering, the fact that we're able to take sewage and turn it into water that essentially doesn't have any environmental impact, any lasting environmental impact when it's discharged into a stream. And so sewage water comes into this treatment plant, and the first stage is to screen out large particles, like sometimes debris will get down into the sewer, like toys and diamond rings and stuff like that. And so this first bar rack here at 1 is just to screen out the very largest particles. And then part 2 is to take out sand and grit and broken up pieces of glass that, if they were left in the water, could cause some scour and erosion to the pumps later on. The third stage is a gravity settling basin that's called a primary clarifier. And the purpose of this first clarifier is for any particles that are still solid in the wastewater. They sink to the bottom. Any kind of grease and oil would float to the top and be skimmed off. And so that sludge that sinks to the bottom is sent into a digester, a sludge digester. The oil is scraped off the top and is treated separately, but then the rest of the water goes into an aeration basin. And so after the settling, there's still plenty of contamination in the water, but it's generally dissolved contamination. Like, it may not seem like it, but even just sugar put into water, if it was discharged into a stream, would be a pollutant. It would cause a negative environmental impact, because sugar, although it's not poisonous to the environment, and although it's not going to harm any aquatic life directly, what it would do is it would deplete the oxygen in the river, because the bacteria that would be breaking down the sugar would also consume oxygen. And that turns out to be the #1 effect that can have a really negative impact on an ecosystem, is when there is a decrease in the dissolved oxygen that fish and other organisms use to live. So what we do to treat the wastewater is we have this aeration basin at a treatment plant where they pump in using blowers and diffusing stones, pump in a lot of air and try and burn up all of that desire for oxygen in the treatment plant, so that when the water is discharged to the receiving body, whether it's a lake or a stream or a river or whatever, when you discharge it into the environment, it no longer needs any more oxygen. And so the reason why I bring it up is that it's important to have a flow equalization basin. Because we're talking about like a bacterial system for purifying water, it's not a system that you can turn on and immediately turn off. It takes several weeks to get the bacteria kind of conditioned and operating in sufficient number and at the right temperatures so that your treatment plant is really removing efficiently all of the pollution that's needed. And so a pretty common thing is to put at the head end of a system like this a flow equalization basin to try and even out the temporal variability in water that's coming to a sewer plant. And what I mean by that temporal variability is, look at this curve, and what it shows is both the average flow and the flow at any given time of the day of water coming to a wastewater treatment plant. And so we humans don't use water in a steady state manner. We use less water in the middle of the night when everyone's asleep than we do in the afternoon and the evening. And so although there can be an average daily flow rate that we'd express, and it would be simplistic to think of that we're using that same amount of water constantly through the day, and our use of water also influences what flow rate's getting into the sewer. And so the continuity equation says that there has to be a balance between the extra water that's entering the wastewater network in the afternoon and the below average daily flow at night and in the early morning hours. And so if you have a big storage tank, then it could kind of tamp out the variations and allow you to meter the average daily flow to the treatment plant, and it would improve the efficiency of the biological reaction. So this is just one application. Flow equalization would allow you to reduce the variation and improve the biological efficiency of the treatment plant. And it turns the peak flows and the minimum flows into more of an average daily flow. Okay, well, that's it for today. We're going to end a little bit early this time. Remember that your next assignment is due on Tuesday of next week. And then a little bit further into the future, our second midterm exam isn't until the 17th of November. So that's not right around the corner, but it'll feel like it. Time seems to be accelerating at this point in the semester. So that's it. If you have any questions, get in touch. And otherwise, I will see you next week. Take care, everybody.